feel free to skip forward. I'm going to derive this, but unfortunately I'll use a differential equation to derive it. But if you want to see some maths, stick around. Otherwise you can just sort of fast forward to see all the equations, But here's the cool thing, right? So you've got this capacitor, it's got charge on it, and if you close this switch, it's kind of crazy. You can't walk through a closed door, but current flows through a closed switch, right? Okay. If you close this switch, the current is going to flow, well, we say conventional current flows from positive to negative. Really, the electrons go the other way, okay? But what it does is it makes this beautiful exponential curve. And the reason for that is if we use the concept of voltage, right? When there's more voltage, we have more current. And current is the rate of change of this, right? So when there's a big voltage on here, right, we have a lot of current, and so it drops steeply. Later on, when there's not as much voltage, then we don't have as much current, so it drops less steeply, okay? Now, if we want to derive this, we have to introduce two concepts. One is that there's something called current, and current is just dq dt, right? It's q divided by t, how much charge flows per second. It's literally in coulombs per second or amperes. Okay. The other concept is the Ohm's law, which you don't understand yet, but here it is. It's really hard. Current is just the voltage or the pressure, right, divided by the resistance. So here's our resistance there. Okay. And then also remember that what the voltage on a capacitor is Q over C. We also need that, right? Now, what I can say is this. I know that in this case, since it's discharging, right, my dq dt is just negative v over r. And I put the minus sign on there because it's discharging, okay? By the way, when it charges, this gets interesting too, but we'll look at that later, okay? So I know that that's true, right? That the rate of current flow off of the capacitor is negative v over r. That's just Ohm's law, okay? All I'm doing is just setting these two equal. Right? I put a minus sign on there because it's discharging, right? But then I also know that that voltage is Q over C, right? So this becomes negative Q over RC, right? So now we've got this thing called a RC, right? We call that our time constant. You'll see that in a second here. Okay, and it actually has the units of seconds, which is kind of cool. Okay. So notice that we ultimately have this differential equation which says, in this case, d, the rate at which the charge changes is proportional to the charge, and the constant is 1 over RC, okay? Just keep that in mind, right? Now, what we do is we guess that the charge on the capacitor is some initial constant times e to the minus time divided by RC, which is our time constant. Now, if we take the derivative of this, chain rule, right, the derivative of the inner function, right, is negative 1 over RC, right, times this outer function. Well, hey, look at that. That becomes, what, Q naught? E to the minus T over RC, all divided by RC. Isn't this thing in the numerator, isn't that just Q? So we end up with the actual expression, right? We guessed correctly. Of course, I knew the answer, so it wasn't really a guess, was it? Okay, so dq is equal to minus Q, right? Because remember, this is Q. We say Q is Q naught e to the minus T over RC. Here's Q in the denominator, right? Okay, that's Q of T, right? A function over RC. So the short version here is that because the rate at which the charge leaves the capacitor is proportional to how much charge we have on the capacitor, we've got a situation that's identical to Newton's law of cooling, where the rate at which heat flowed out of that boiling hot water was proportional to the temperature of the water, which is super cool. So let's look at the formulas that we've got, and these are for discharging the capacitor. Charging is slightly different, but for discharging it, we've got, this is the one we derived, but all I have to do is just divide both sides by C, and I've got this guy, right? Okay, and then all I have to do is divide this by R, You don't know this yet, but let's see, I is V over R, right? And then I get this guy, okay? So everything about a discharging capacitor, the voltage across it, the current, the charge on it, the current flowing out of it, decays exponentially, just like this. Notice that there's like a little shorthand thing going on, so that little tau, substitute RC, that's our time constant, okay? Now, notice that R is in volts per amp, right? Coulombs, capacitance is in coulombs per volt, right? So if we multiply those units together, right, we get volts per amp times coulombs per volt, right? And we'll end up with, well, the volts go away. We'll end up with coulombs per amp, right? Well, an ampere and other units for it are coulombs per second. So coulombs over coulombs per second is just seconds, right? So literally this time constant is in seconds. Okay, that's the R times C is in seconds. If you look at this, that exponent there is negative T over tau. It's seconds over seconds. So that exponent is a pure number, and all such exponents like that in actual proper physical equations are pure numbers. And the same is true for the arguments for like cosine and stuff like that. Whatever you put in there is a pure number. It has to be a pure number. Remember, radians have no units. This thing also has no units. It's a pure number. Okay, pure. Let's use this. Let me use this in an example for you. Oh wait, before we do that, let's look at charging. Okay, if you charge, all that happens is we just use the same formula, only it's 1 minus this thing. And so you get a voltage that does this, right? But what's cool about a charging capacitor, so if we charge it, right, we close that switch and now this potential source flows through the resistor and then charges our capacitor, okay? What's cool about this is that the potential goes whoop, it changes quickly at first because there's no charge on the capacitor. But as charge builds up, a potential exists across the capacitor that opposes that flow, right? So it does this, right? But notice the current still does this, which is, I looked at that and I'm like, well, they got that wrong, but they didn't, right? Because here the voltage is changing quickly, which means that our current charge has to be flowing onto the capacitor quickly, I feel, right? Okay, so that makes sense. So notice that the voltage goes like that, which is just this, right? But our charge on the capacitor still is I naught e to the minus t over tau, where tau is. Got a fine haircut, right? It's got the wavy hair. It's a Greek letter T. Okay. So charging, and I don't know if they don't give you the formulas for charging, so presumably they're not going to give us problems with it, but they might ask you a conceptual question. So I just thought I'd show you that. Okay. So let's take a look at an example problem. This is a discharging one. Okay, so a 47 microfarad capacitor is charged to 12 volts initially and discharged through a 100,000 ohm resistor. Okay, so R is equal to 100,000. The capacitance is equal to 47.0 times 10 to the minus 6th farads. Okay, so RC is equal to, we can do this. Okay, RC is equal to 100,000, okay, times 47 times 10 to the minus 6. Let's see what that is. 100, whoops, gotta turn my calculator on. 100 times 47 e minus 6. That is 4.7 seconds. Okay, and what that means is in 4.7 seconds, the value on that resistor is going to be reduced to 1 over E, which is about 0.368 times whatever the initial voltage is, right? The voltage, so whatever that initial voltage is will be reduced to about 0.368, which is 1 over E. That's just what it is. So it says, what is its voltage 13 seconds into discharge, right? So I'll use this guy, right? V is V naught e to the minus t over tau. right? So that's going to be 12 volts times e to the minus, what time is it? It's 13 seconds divided by 4.7. We could do that. When we get to nuclear decay, we'll end up with something like that called a half-life or something like that. But this is, kind of like the idea. This isn't a half-life though. Okay, hold on. So 12 times e to the negative 13 divided by 4.7. And that voltage is 0.754989. So 0.755 volts. At 13 seconds, it will have dropped to 0.755. So if we draw a graph of this, right, here's 12 volts, right? It's going to be like, it's going to be very low, right? Here is, whoops, my axes are not level. Anyway, that's the idea, right? So then the question is, what time does it take to reach 6 volts? This would be like, if it's nuclear decay, the half-life of it. Okay, so we can do that too. So we're going to use the same equation, right? V is V naught, e to the minus t over tau, right? And I'm just going to plug in numbers. So 6 equals 12 e to the minus time that we don't know over 4.7. We can do this. I'm going to do, let's see, what's my next step? 6 twelfths. I'm going to find the natural log of that. Okay, that equals what? Negative t over, and then t is equal to 4.7 times the natural log of 12 sixths. And you're like, what happened to the minus sign? I just took the inverse of what's in the natural log, right? Isn't that true? Natural log of a is equal to the opposite of the natural log of 1 over a. I remember that. I think that's correct. Let's see if it works. Times the natural log of 12 divided by 6. Could have just put a 2 in there, but 3.2577 seconds. I stand by what I just said. 3.26 seconds. These aren't too hard. I don't know. We get used to them. Once you learn this, once you can do these problems, you'll be able to do problems with like exponential decay for nuclear decay. So your learning won't be just for this, which is fairly obscure. Anyway, I think that's all I have to say.